Over the past decade, the nature of human information has transitioned into a state that functions with a different set of rules, a shift that occurred while most of us were still treating data as a simple ledger. For decades, data was a retroactive byproduct. It existed as a passive collection of historical figures that documented what had already happened in a business or a laboratory. Today, data functions as an active, predictive asset. It is an engine driving automated decisions across global networks in real time. Data science is the specialized discipline engineered to bridge this gap, translating chaotic raw information into actionable foresight. The field has transformed data into the raw fuel for the systems that determine what will happen next. Data science occupies a specific space between disciplines. Its scope exceeds standard statistics and requires a technical application broader than software engineering. It requires a convergence of three distinct areas: statistical theory, computer science, and deep domain expertise. Only by overlapping these separate disciplines can we extract actual meaning from increasingly complex information. To understand how modern artificial intelligence predicts the future, we must reverse engineer this architecture by tracing its chronological evolution. Missing a single step in this progression makes it impossible to understand the mechanics and the constraints of modern algorithmic power. Before the 20th century, data analysis was a manual process, strictly governed by the rules of classical statistics. This graph illustrates how early methods summarized historical data, allowing researchers to plot basic patterns. These descriptive statistics provide a view of the past, but the model stops entirely at the present. It lacks a mechanism to automate or project into the future. Human capacity created a physical bottleneck. Manual calculations limited the size and complexity of the data sets researchers could realistically process. While foundational for scientific rigor, pure statistics remained backward-looking, constrained by the speed of human calculation. The first major accelerant arrived in the mid-20th century with the invention of raw computing power. Early automation required massive hardware, filling entire rooms to execute faster calculations on larger datasets. It was during this period, in the 1960s, that the specific term data science first appeared, though it remained a niche academic concept. At the same time, physical data storage scaled up, moving from paper ledgers to banks of magnetic reel-to-reel tape drives. Despite exponential increases in mathematical processing speed, the discipline remained reactive. The hardware alone could not produce predictive autonomy. This changed in the late 90s and early 2000s, when the internet boom triggered an exponential accumulation of digital information. The data itself mutated. We transitioned from clean, structured numbers to a chaotic flood of unstructured text, video, and social graphs. As internet access spread, individual interactions became a primary source of mass public data generation. The mobile revolution accelerated this, turning human behavior into a measurable, harvestable resource. Pure statistics broke down under this unstructured volume. Organizations had to build cloud computing and massive physical architectures to house the avalanche of data. Acquiring mountains of unstructured information created a massive liability unless a new computational method could be developed to extract patterns automatically. That solution arrived in the 2010s, as machine learning and artificial intelligence emerged to solve the big data bottleneck. The critical mechanical distinction here is the loss of rigid rules. Engineers stopped programming static instructions and instead deployed algorithms designed to self-improve based on the data they ingested. This structure visualizes a predictive model ingesting unstructured chaos on the left, organizing it into clean trend lines on the right. Through this continuous loop, the model learns. Adapting its trend lines autonomously, the system moves from describing the past to automating future decisions. Machine learning is the component that completed the transition, turning data from a historical archive into an active predictor. Zooming out, we can see the fully constructed data science architecture: domain knowledge, statistics, big data infrastructure, and machine learning algorithms. This integrated engine is the practical, operational force reshaping global industries. It dictates the efficiency of global logistics networks and personalizes the user experience in retail e-commerce. We see its impact in high-stakes domains like healthcare, where predictive modeling on medical data improves patient diagnostics. Theoretical data science has matured into an operational tool that dictates the physical logistics of the modern world. However, relying on automated, data-driven decisions introduces severe vulnerabilities to society. Because these algorithms train on historical data, they adopt the flaws of that data. They can mathematically scale and hide systemic human biases. A flawed algorithmic model can instantly tip the scales of fairness, causing catastrophic, irreversible damage to marginalized populations. Algorithmic transparency, data privacy, and ethical oversight have moved from theoretical concerns to urgent operational requirements in modern business. In just a few decades, humanity moved from manual ledger entries to self-updating predictive neural networks. As artificial intelligence, the Internet of Things, and quantum computing continue to converge, this predictive architecture will become more deeply embedded in our daily lives. Understanding the architecture of data science is the essential literacy required to navigate the future.